wanted to share with you a little bit about what the Spintron is and why it's valuable and how maybe even you can use what we learned from it to help you in your engine shop. So, for years, engine development was done by the seat of the pants. We'd build an engine and you'd run it on the dyno, you'd go out to the racetrack with it, and basically you would change parts and hope for the best, and sometimes it ran better and sometimes it didn't. But like many things in the industry, technology has changed and keeps driving what we're doing. And so the Spintron is one of those pieces of technology. Now, maybe you're new to engine development and engine building, you don't know what a Spintron is, or maybe you've heard about it before, but you're not really certain how it works or what it does. Well, that's the kind of stuff I wanted to talk to you about today. So behind me, we have our Spintron that we have here at EFI University. And basically what this thing is it's a simulator. We can take most of a complete engine and we can simulate how we would run it on the dyno, on the straight racetrack or whatever, except that because we're not running the complete engine, the parts that are missing allow us to go in and investigate, sometimes in real time even, what the engine's doing. So for example, the most common use of the Spintron is to develop a better valve train. So if you think about what the engine's doing, we always say, well, the engine's an air pump. We got to open the valves to get air in. We got to close the valves and keep them sealed tight while we do our combustion process. Then we got to open the exhaust valve and we got to get it all out. The timing of those events, when they happen, where they happen, how quickly they happen, have the most influence, or the signature, if you will, on how the engine actually behaves and performs in real life. The problem is there's a little bit of a disconnect between what we theoretically design. For example, if I get a cam card and I look on there, it'll tell me things like valve lift, duration, lobe intake and exhaust centerline angles, lobe separation angles. They give me all this stuff on the cam card, and then what I do is I assemble it in the engine, and I put my degree wheel on, and we go in there and we make sure that it all matches the cam card. The only thing is that when we actually run the engine, it's dynamic and it's variable, and it doesn't stay static like it did on my engine stand. Things bend, things flex. When they flex and bend, they can rebound at a different time, and so all throughout the RPM range that you run the engine, this dynamic sort of movement of instability of parts and going in and out of being a stable, good working valve train actually affects the engine's performance. If you think about it, while we're trying to get air into the engine, and we have the valve lift curve plotted something like this. So this would be like what the lobe of my camshaft might be producing at the intake valve. Well, I can only move air into the cylinder when the valve's open. So it should follow then that how far the valve is open also affects how much air I can move into the cylinder. But what really tends to matter to the engine more than that is the relationship of how fast that cylinder is asking to be filled. That's the demand side, and how much area we have to try to fill the engine is the supply side. So think about it like a study in economics where supply and demand have to be well matched. So anywhere on the lobe here that we are, the piston's going to be at a specific spot going down the bore, and that supply and demand need to match. Well, if I get the perfect camshaft theoretically matched with the perfect valve spring and the perfect rocker arm and the perfect push rod, we could go in here and say, boy, that all looks great. Now the problem is when I start running the engine, if, for example, my valve spring can't keep up and it doesn't have enough force to hold everything in place, maybe I end up getting more lift over the nose than I want. Or maybe it comes down and it doesn't stay on the seat. It hits the seat and it comes flying back off the seat, and we call that valve bounce. Well, we would never really know that in the past. We just ran the engine. It was either good or it wasn't good, and we would change parts until we got what we wanted. What the Spintron does is it's a machine that allows us to look at and measure and create data about the behavior of the valve train as the engine's actually running. So behind me, you see some of the pieces of it, and we'll go in there and look a little closer in a little bit. But it's about the opposite of what you would expect from a dyno. Typically, we build the engine, and we put it on the dyno, which is a power absorber, and we run the engine, which spins the dyno. The dyno creates load, and it records things like power and torque and RPM and all sorts of other data. The Spintron's the opposite. We have a big electric motor in the Spintron connected to our engine assembly, and we can then use the electric motor to spin the engine. That way we don't have the combustion process taking place. We don't need the water, things like that. It's mostly a complete engine. We typically don't have the actual crankshaft or the pistons or connecting rods. Now here's the cool part. Since we didn't have a real piston and connecting rod and an actual crankshaft in there, it means that we don't have combustion, so we don't need things like the water jackets to be full of water. Since we don't need the water jacket, then we really don't need the side of that cylinder wall. So what we typically do is we'll have a dedicated, like a test block, and we'll take it and set it up in the middle, cut a big hole in the side of the cylinder, and that gives us access to the cylinder while the engine's basically running under simulation. So as the electric motor now is spinning all of the parts in the valve train, we can take a laser and stick it in there, and that laser can point straight up and watch the valve. That's where we get this plot here from an actual electronic measurement of how the valve is opening and closing and how fast and how far. And that allows us to really start taking data-driven decision approaches to what we're going to do in the valve train. If I take a rocker arm, for example, and I got one that's made out of aluminum, there could very well be a difference for the same camshaft and same lifter and same pushrod in the engine. There could be a difference between my aluminum one and if I change it out for a steel one of the same size and design. We would be able to see that throughout this lift curve because we can measure it in real time dynamically. Now what I mean by dynamically is, for example, I have a plot here that's taken at 1553 RPM. So if I use that as my reference, what happens is as you start to drive the engine faster and accelerate it faster and move things, you tend to get more forces generated in your dynamic system. And so what happens is things start to change along the way. I'm going to scroll over here a little bit and show you, for example, what this particular one looks like at, say, 6,300 RPM. I'm not sure how well you can actually see this on the camera, but what I see when you zoom in here is this yellow line is the trace that actually shows us what the valve was doing on that engine cycle. And it does a measurement of every single crank degree, that's 360 measurements, at every single engine revolution. So we can plot out what was really going on there, but you'll notice the purple line stayed down here at that 1500 RPM reference. So what we see here is a little bit of flex or bend somewhere in the system right at the opening. So we have to start asking ourselves, how do I solve that problem? And that's when we go to work. We go in there and we check valve lash and we try different valve spring settings. We can shim them up or we can take the shims out and stand them up. We can change the diameter and thickness of the push rods. We can change the lifter configurations. I mean, ultimately we can even change the shape and the profile of the camshaft lobe that's driving all this stuff. But again, it's finding balance between all of those forces and factors that gives us the best approach to making our engine run the way we want. Sometimes what we're looking for is just a stable system. Other times what we're looking for is to know what the limit speed of the engine actually is, where we say, okay, I can turn this engine all the way to 9,000 RPM and it's stable, but by the time I get to 9,200 RPM, it's not stable anymore. So people always ask me, well, how do I know what the rev limit of my engine is? There's a lot of factors that determine that, but certainly one of them would be when your valve train goes out of control, it's probably time to start revving the engine up because you absolutely won't have parts that last very long that way. And you typically also cannot make very much power that way. Think about it. If the valve motion, which is our supply side, is not keeping up with the demand side because the valve isn't actually following the commands that the camshaft is giving it, whether that's from flexing, whether that's from the valve spring not having enough force, or maybe it comes all the way up and it comes all the way down and closes, and then it bounces off the seat again and it goes open simply because we didn't have enough valve spring pressure to keep it closed. When that happens, the performance will always suffer. Now in the old days, we just used the engine dyno. You could see it, the power would go up, and all of a sudden it would just drop very sharply and precipitously. We'd have this huge dump and you're like, geez, what's going on? And oftentimes we would find it was the valve not staying closed. Let me give you an example of that. So if I scroll over here, we can see when we go up here to the limit speed of this particular combination. Now I see quite a bit of bending and deflection on the opening side. Things kind of normalize and it catches back up as we go over the nose. And then it sort of tosses off a little bit or kind of floats down the back side of that ramp. And it comes down, it crashes, and then you see this yellow line, it goes boop, comes back up again. So if I zoom in here and kind of look at what's happening, what I could see, if I go over here, is that the valve closes here at about, just to keep it simple math here, about 165 degrees, and then it bounces back off the seat about 13 thousandths of an inch Doesn't close again until I'm at about, let's just round it off and call it 205 degrees. That's 40 degrees of duration that the piston was moving and the intake valve wasn't all the way closed. So let's think about that for a second. Let's say that typically, a really stout race camshaft, maybe you look at your cam card and it says, well, the intake valve opens, 20 degrees before top dead center, and it closes 60 degrees after bottom dead center. So now you think about that piston, was at bottom dead center, it's some distance up the bore now by the time you've got 60 degrees past bottom dead center. Well, what we just saw there is, well, shoot, now it's bouncing for another 40 degrees. So that means I'm really 100 degrees after bottom dead center before I'm totally sealed in that cylinder. Now keep in mind that entire stroke for compression is only 180 degrees. Well, we just lost the first 100 of them. And now let's think about it. Typically, I'm going to fire my spark plug before top dead center, let's say 30 degrees. That means I really only had 50 degrees of total time to compress the mixture before I lit the spark plug. Well, you can understand why when that happens, the engine's performance drops off like crazy. So for obvious reasons, we want to try to avoid that. But in the past, the only way we did is we just ran the engine till it stopped making power, and we'd make a change, try a different spring, try different push rods, whatever. This machine, the Spintron, allows us to dynamically and in real time measure those things. Now, we could develop a whole Master Series course on the finer points of what's going on and what to look for and how to do it and talk about velocities, accelerations, and jerk profiles. But I don't think that's a really good conversation to have just yet. What I think we ought to do is take a closer look at the machine itself and some of the hardware so you can get a better understanding of what it is and how it's doing what it's doing. Want to take a look? Let's go in there and we'll have a shot. Okay, so now we're inside the test cell for the Spintron, and what you see is mostly a complete engine. Now there's no intake manifold, no fuel system, no ignition system, because we didn't need that. Now on this particular engine, it happens to be direct injected, and so that means we do have a mechanical fuel pump here that goes through and gets driven off the camshaft. Anything that's being driven off that camshaft, we want to make sure is attached to the engine, so we're testing. But it doesn't have any pistons or connecting rods, just a straight mandrel, a straight shaft that goes through and the bearings clamp just like they would on your crankshaft. And then, of course, your balancer and timing assembly and all that is installed. Now, the machine part of it is actually a giant electric motor. And there's different size ones. This one's kind of in the middle at 75 horsepower. That takes about 480 volts at about 130 amps maximum current. So it's the kind of thing that you don't want to get too close to because it won't shock you, it will vaporize you. But it's very powerful. And so what we then do is we create a series of tests through the commands on the console in the computer out there. Those commands come through into what's called a variable frequency drive. That takes the electrical current from the building and modifies it to control how fast the motor spins inside the box. So the big giant electric motor is in here. It's got a coupler. We're basically bolted to it just like we would be on a dyno, and we can spin the engine just a little bit. We get all done talking about it. I'll take you guys for a ride on this thing and we'll see what it's like. But one of the things that's generally surprising to people the first time they see an engine on the Spintron is how much noise they make. The actual mechanical lifting and opening and closing of valves and the valves coming back on the seats and spring and lash and all those things, it literally sounds like the engine is actually running, even though that's impossible because there's no spark and no fuel in there. It will typically sound like it's running. So in order for that to happen, we still have to have all the lubrication for the engine. So we can either run a dry sump system that is included in your engine package. I also have a dry sump system that I run off the machine. So I have an electric motor to a set of pulleys that runs an actual dry sump oil pump. And then I've got a sump can over there and some feed lines and everything. Or we can run it like this engine, which is just a factory wet sump using the factory oil pump and supply and everything internal to the engine. So a lot of flexibility there. The thing about a Spintron is when we think about it, most people want to talk about the cool stuff, the valvetrain, dynamic stability, all that kind of stuff. But man, there's a million other things we could actually use this machine for. We could use it to test pretty much anything that spins on the engine. Want to test the efficiency of your alternator or water pump or the pulleys or the friction of your bearings, any of that kind of stuff? We can rig up a way to test it here on the Spintron. And so it's not always just about finding limit speed or always just to find dynamic stability. It could be, for example, about durability. Maybe I have a system that I know is pretty good, and I want to make sure that it will go all the way till the end of the race. We can set up the test sequence to look just like the racetrack. We can include gear changes, throttle blips, just like you could, like you're looking at the data log in the car. And oftentimes we'll do that, and we have to use an engine for a customer where we don't have a dedicated test block where we can just cut a hole in the side of it. So we have to use their real parts. Obviously, when we do that, we have to be careful with the parts because we don't want to break them or damage them or whatever. But what it allows us to do is run the engine and then stop and take it apart and look at it. For example, I could come over here, I could zip the valve cover off this thing, and then I've got my feeler gauges here. So I got kind of a go and a no-go. This is, tighter than that's too tight and looser than that's too loose. And we've got our torque wrench that we use, and it's got an Allen key in it. So we just come over here, we grab our wrench on the crankshaft, and we roll it around to where I'm ready to check my lash. Take my lash tool. Okay, that's good. Move to the next one. We'll do that often just to make sure that we don't have any issues with reliability or stability in the valve train, especially on engines where we don't have the ability to use the laser for dynamic tracking. You can do a laser, you could put a high-speed camera in here. The possibilities are endless of what you could learn with a Spintron, which is exactly why we do it. Part of our competition engine development training program here at the school is exposing people to the level of engine building technology that you can't get a lot of other places. But that doesn't mean it has to be a rocket science, NASA type explanation every time we use it. Sometimes we just want to run it and make sure the engine will last, and that's what we might do this for. So typically, we'll get everything set up, we'll run our first test, we'll pull the valve covers off and just check around and look for stuff. We look for those high danger items, things like, wow, all of a sudden I got a ton of valve lash that I didn't have before. Do I have a push rod tip going away, or a lifter that's damaged, or something happened that I didn't catch, right? I might go through, check all the lash, and as I'm looking, I go, oh darn, there's a little chunk of valve spring in there. That means something's really unhappy. That gives me an opportunity to stop now. And if all this seems complicated and complex and like it's a ton of work and it's expensive, well, you're right, it is. However, in my way of thinking, having access to the Spintron data actually makes engine development work extremely inexpensive. What do I mean by that? Well, if you think about it, let's say a guy came and he had a very high-end engine package. He might have a $60,000, $80,000, or $100,000 engine that he wants to make sure stays safe and stable. Well, typically, because there's no pistons running in the engine, if I make a mistake, we can do some damage. We could drop a valve, you could bend a push rod, maybe break a rocker arm. But honestly, if it spits a valve out, it falls down into the engine, and we go in there and get it and clean it off, and you can most of the time, put it back in because it didn't crash into a piston like it would have if we skipped this step and we took that $60,000 or $80,000 or $100,000 engine and we just assembled it and put it on the dyno. Then what happens, we run it on the dyno, if it drops a valve or breaks a rocker arm or whatever, it's catastrophic. You think about Project Spinal Tap that we did, which was an inline valve, LS7, sort of small block deal. We took that thing over 11,200 RPM. You're talking about opening and closing that intake valve like something around 95 times per second. You don't have to miss by very far or be wrong for very long before you've destroyed just about everything in the engine. And so the cost of having a catastrophic failure on the engine dyno can be avoided or mitigated by spending, $2,000, $3,000, $5,000, $6,000 up front on the testing here. Now, if you think about the next step, let's say that I'm in too big of a hurry for that. I assemble and build the engine. I don't want to waste time on the dyno, so I just put it in the race car. Well, now you go out there and you got $250,000 to $500,000 invested in a race team, race car, hauler, trailer, whatever. Your first pass down the track, it drops that same valve, except now it locks up the piston, it breaks the connecting rod puts a hole in the engine block, that puts oil on the track, car drives over the oil, next thing you know, the car's upside down, it's a total loss. To me, this $5,000 or $6,000 of testing was absolutely dirt cheap. So one of the things that the Spintron does for us that gives us confidence is that oftentimes our high-end drag race engines that we build here at the school, they'll go on the dyno and we'll warm them up and then we get ready to do a test. Well, the start of our dyno pull is often 8,000 or more RPM. That's the beginning of the test. And we might rev it up to 10, 10.5, 10.6, sometimes 11,000 RPM. And having the confidence of knowing that the valvetrain was already tested here in a much safer environment, it gives you a lot of sort of, warm and fuzzies to open that throttle the first time and do that. And then, of course, if it lives through the Spintron, it's probably going to make it through the dyno. If it makes it through the dyno, it's probably going to make it down the track. And so we gain the success long-term at the track in baby steps, incrementally improving our system, starting with real data, developing a system that proves itself here, then we add combustion, then we add competition. Make sense? So if you guys want, I'll bolt this thing back together. I'll walk around to the other side. We'll close the doors up here, and I'll take you for a little ride. All right, guys, so we're back out here now on the control side of the Spintron. And I've got a couple monitors, and you can see the engine there in the background. You'll probably even be able to hear it pretty well. On the left side, what I have is my control side. This is the side where I type in stuff to tell the electric motor what I'm trying to simulate, what engine speed I want to see at what time. And we typically will do this kind of like a dyno pull, where we'll start up and kind of start out slow, and then we'll ramp up. And that's what I'm going to do for you today. But we can also do racetrack simulations with gear shifts and throttle lifts and whatever else we want, as we sometimes find that there are advantages to paying attention to the finer points, the stability of the valvetrain to recover during a very fast negative transient, say like a gear shift, where you might be at 8,000 RPM and 0.2 of a second later you're at 5,000 RPM. So that jerking of the crankshaft, timing chain, timing belt, all that stuff being jerked back the wrong direction sometimes can upset the valvetrain. So we look for that kind of stuff. But today what I'm going to do is just set up a basic run. We're going to sweep this thing. We'll start out at kind of hover around 1,000 RPM and let the oil flow through it and everything get moving. Then we'll accelerate up to about, 6,800, 7,000 RPM, something like that. We'll bring it back down, and then we'll stop, and I'll show you some of the data. But you will see the data in real time. So the benefit of that is when I'm running this thing, I'm looking for key points. I'm looking for deflection. I'm looking for loft. I'm looking for bounce. I'll show you some of that stuff in the post data. But it allows me to have my finger on the button over here and go, look, if I see something or hear something or, end up something I don't like, I can just stop the test. So hopefully that won't happen in today's test, but we're going to take a run at it and let you guys see. So come along with me. I get everything set up here, and I think we're just about ready to go. So click go, and yep, everything looks good. So up here you can see my valve trace, and my RPM's about 1,000. It's scrolling across in the time over here, and about another 5 or 6 seconds here, it's going to start to accelerate, and I'll be watching. All right, here we go. So that was a pretty good test. I'm going to stop everything here, and now we can take a look at some of this data. So I'll come down. I'm going to switch our view here, make my X range something we can see. Okay, so now I can look here and say, okay, that's where I was 1,000 RPM, just kind of warming everything up, and that lasted for about, 15 seconds or so. And over the next, maybe 15, 20 seconds, we accelerated from 1,000 all the way up to, we saw 6,850 RPM. So I can pick anywhere along the way. I can zoom in on that, zoom out on that. But what I'm going to do, I'm going to start here, and I'm going to make that 1,000 RPM my reference. I've now turned it purple, so that now as I sweep through the RPM range, I can see the difference between what the valvetrain was doing at that specific RPM versus what it was doing when there wasn't a lot of load on it, say at 1,000 RPM. So as I sweep through here, if I pick a spot like, 6850, it's a nice easy spot. The first thing I notice, and I do that, is darn it, sorry, I did that again. I come over here, there's a lot of bending and deflection somewhere. Now that could be a number of things. That could be my push rod, the rocker arm. It could even be the bolt that goes down through the rocker arm and holds it into the cylinder head, trying to pull the threads out of the cylinder head. There's any number of those things that could be doing that. Over the top here, you see that if we look in real close, there's actually a little bit of wiggle or bounce or whatever, and some of that can just be valve spring fluttering back and forth. The valve spring gets into kind of a surge state, and we'll get a little variable lift there. In severe cases, we'll even get like golden arches like McDonald's, where it's actually bouncing the lifter off of the lobe of the camshaft. We don't like it when that happens. And then coming down the backside, you can see we have a little bit of loft there, which might even be a little bit of phase shift that we're seeing in the laser possibly. But then we look down here at the bottom, and it comes to a close. And other than maybe a couple of thousandths of an inch or something, it looks like the valve closes and stays closed pretty good there. Some of that, we even see like negative numbers there sometimes. The head of the valve will come to the seat, and it'll almost do like an oil can and go boop, 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 like that. And you'll see a negative number there where it's bending that valve under the spring force trying to hold it on the seat. And so basically that's what a Spintron run looks like. And we go through and evaluate the shape of that lobe. And we can do things like calculate the velocity. And if you're not real good with your calculus, the velocity curve you're seeing here in blue is simply for any given point in time anywhere on the lobe. What we have in the lobe is the lift at every point. But if we take the lift at this point and measure the difference between that lift and the lift at the point right before it, what we would get is the change in lift over the distance we covered. So it'd be like feet per second, miles per hour. That's a derivative that we call velocity. So in this case, the velocity is how much lift we're getting per degree of crankshaft rotation. And we can look in here and see that it maximizes here about a third of the way up the opening ramp at somewhere around 7 1/4, 7 1/3, 7.3 thousandths of an inch for every degree of crank rotation is how fast we're accelerating there. Then you can see as we go over the nose, we're basically zero. Our speed is zero because we're not going faster or slower. And then, of course, it starts to go negative until we get back on the seat. So we can look at the velocity as the derivative of position on the lobe. Now, once we've done that, we can come over here, for example. I'll double-click here, and we'll set up this one here as the acceleration rate. So since we're doing our calculus class, my mathletes out there, you guys will know that acceleration is the second derivative. So now what we're talking about is how fast the velocity is changing. So you think of velocity as miles per hour. You go, well, there's 30 miles an hour and there's 60 miles an hour. And everybody kind of knows that 60 is faster than 30. But what acceleration is measuring is how long it took you to get from 30 to 60. So if I went from 30 miles an hour to 60 over the period of an hour, you wouldn't even notice it. But if I did it in 1 second, you'd be glued to that seat and going, hey, this is a pretty good ride. Well, what I can plot on my screen here is how fast the velocity of the valve was changing. And so we can see as things change and get higher in RPM range, you see those lines really start to wiggle and move around. And when they get the valvetrain into distress or in harmful situations, we see immediately where we get these huge spikes in acceleration and velocity. And then, of course, there's more derivatives. We can look at jerk, snap, crackle, pop, if you can believe that. Those are all derivatives that we talk about. But for the most part, we're looking at the valve lift. We're looking at the valve velocity, how fast that valve is moving. And we're looking at the acceleration rate of the valve to tell us when we get it just right. So I know that some of this seems complicated, but hopefully what you take away from this is that we can use this machine to make the engine better. And when we do that, we can put it on the dyno with confidence and know that we're not going to hurt stuff. So if you want to learn more about this, I can spend days talking about it with you at one of our classes here at the school. And of course, I'd love to meet you and have you come. But for this seminar, I think we've got a lot for you to chew on. So I'm going to open it up and let you guys ask some questions at this point.
Welcome back, Joe Castello, Lake Speed Jr. Where would we be without the Spintron?
Oh man, it's the Spintron was one of the key developments in NASCAR valve train technology and development. That's how we were able to reach engines that could turn 10,000 plus RPM. So it's really cool is the fact that a guy like Ben has one at his shop.
Yes,
because that's technology that was always locked behind the doors.
And isn't that what we've been talking about? Like the transfer of technology from these far off distant locations like Formula One level to normal guy level, and then we can really put it through his paces. Of course, Ben Strader, EFI University, is joining us virtually, part of the Engine Performance Expo. Ben, welcome. How are you live? How are you doing?
Hey guys, how's it going?
Doing great. Super great. Loving your background. So far you win the boat in the background game.
Exactly.
Yeah, I decided everybody else's was pretty boring, so I should put some flash in mine so you didn't have to just stare at me the whole time.
Throwing out the gauntlet for tomorrow. Someone's going to try to one-up them. Definitely enjoyed the...
I think Kazi's up tomorrow. He has all kinds of cool stuff, so he'll show me up, I'm sure.
Exactly.
Fired the shot. Exactly. Fired the shot. Really appreciating the information. Now is the opportunity for everybody who just watched the video to ask some questions. So put your questions in the comments section, everybody, and we'll pose them to Ben. But we're going to be spending the next hour or so with Ben, because after our Q&A, we're going to throw it back to another video where we delve a little more deeply into some things. So, Ben, we got you for the next hour. Are you ready?
Yeah, I'm just here hanging out in my garage at home, and I got nothing better to do than hang out with all of you guys.
Excellent.
Oh, good. So, Ben, so to kind of follow up your Spintron segment on the heels of Billy talking about low shock technology, expand on that a little bit. How can you see that with the Spintron? Because yesterday, Randy Neal was giving a really great talk about engine balancing, and his whole thing was about if you don't have it in balance, you're going to create these harmonics, and that harmonic, that vibration, isn't just going to stay in the crankshaft. It's going to kind of propagate its way throughout the engine and cause havoc everywhere else. I think he said it was like having a tiny baby with a hammer.
Where does he come up with that? A little baby with a hammer smashing the inside of your engine. It definitely was a horrible analogy, but it'll stick with you forever. So what about that, Ben?
Well, it's funny. I don't even know if I knew what low shock technology was until I started hanging out with Billy, specifically when we worked on that Spinal Tap project. And, it became clear really quickly early on in that that we needed to be careful with how you upset the system. If you tick that thing off, it doesn't just recover on its own. And so I think, the Spintron was like the ability to almost have X-ray vision and see inside the engine almost. To me, it felt like, we could immediately tell when it was misbehaving or when it was upset. And so it probably saved, who knows, countless amounts of money, thousands of dollars, certainly, even through the failures we had. But the ones that we didn't have because we could see the system getting excited and getting out of control. Well, low shock technology has just basically grown and furthered that whole idea. And for me, that project inspired us to buy the parts to kind of build our Spintron and make it what it is, what you saw in the video there. Ours is a little bit different than most of the ones out there, but it was the keys to the kingdom, really. The idea of running an engine, 8, 9, 10, 11,000 RPM on the dyno was totally terrifying before Spintron, at least in our shop, before we did the Spinal Tap project. And for us, the combination of understanding why we needed to look at that stuff with the Spintron and understanding a little bit more about the low shock concept has just, I don't know that we even do hardly anything anymore that's not low shock, to be honest with you. It's changed everything for us.
Wow, tremendous. All right, we got some questions coming in. I do like how Ben mentions, though, like the idea of being in a dyno room, period, is terrifying. People don't think about
$11,000.
People don't think about that, right? Like, you're in there with that thing, man, and you never know what's going to happen. It's obviously exciting. But all right, here's a couple of questions.
I know, I wouldn't stick my finger in an engine. I know that.
Yeah. Little tease for tomorrow. All right, Rich wants to know, can a Spintron be used to seat rings to bore for break-in? Lake, of course, you're going to know a lot about that. That's first up.
Well, no, because the problem with the Spintron is there's no piston in it.
Right.
So,
there it is.
Right.
Excellent, excellent. Next, to test an engine that will have boost, do you need to add or, I guess, simulate boost on a Spintron?
Well, we get that question a lot, and frankly, I think it's hard to argue with the logic of it, that if you're going to have, a lot of guys say, what about the pressure that's trying to push that intake valve open? You're not simulating that, and it's hard to argue with that logic, but I think what a lot of people miss there is that boost pressure didn't get there for free. Like taking, for example, a turbocharged engine, yes, we're going to have 10, 15, 20, maybe 30 or 40 or more PSI pushing that intake valve open. But don't forget that we also are exposed to the exhaust pressure in the system that's on the other side of that valve. And so it's really the differential pressure across the valve that matters. And generally speaking, in most turbocharged engines, you're rarely in a situation where the boost pressure is significantly greater than the back pressure. So if anything, we're going the other way. All of that said, we get a lot of those questions a lot. What about boost? What about engine temperature? What about this? There's a lot of guys playing the what about game, and it's usually guys that say, you're wasting your time, or that effort is not being accurately used. But I guess my argument would be that while all that is true, we're not simulating everything you could simulate with a running engine. That's kind of the point. We're trying to isolate these variables and fix them before we go to the engine dyno and risk other unknown catastrophic failures. So kind of two answers in one there for you, but I think the value of the Spintron has been proven over and over by guys that are building engines that cannot afford to lose them by a failure after the fact.
That's the biggest point, and you made that point in the video, that it's way cheaper to find that problem and fix it on a Spintron than it does at the racetrack, because the casualties that are suffered at a racetrack because you have all of those other collateral damage,
Sure.
That's the big money.
I mean, I think about how many guys have ever hit the wall because they kicked the rods out, So why am I fixing fenders? Well, because I had an engine failure and I drove over my crankshaft. So we'd rather avoid that as much as possible. And the Spintron's just one piece of the puzzle of why and how we do that.
Hey, the Spintron, there's already a hole in the side of the block. I mean,
There you go.
Yeah.
All right, Pat wants to know, he's excited about it, and he's sold on the deal. So he wants to know, what's the expected hourly rate to use a Spintron? And are there any shops that you know of or recommend in the Missouri, Kansas, Oklahoma area?
Oh, that's a good question. So I don't think you'll find, first of all, there's probably not a ton of shops available that have a Spintron that typically make it available to the public, mostly just because they're so busy doing their own stuff. There are a number of great places out there that do that kind of work. I know a fair amount of places that will, but I don't think you'll typically rent it by the hour. It's not like a cheap hotel, it's pretty much a day kind of thing, mostly because it takes so long to do the setup. And then if you're going to use the Spintron effectively, it's a matter of, testing, changing some parts, testing something else. It's an iterative sort of process, and it's typically not something we run for half an hour or an hour or 2 hours or whatever. So it's a multi-day process using, I think that engine that was in the video there, we went through 10 different valve spring configurations, 2 different rocker arm configurations, and several different pushrod configurations, trying to find the sort of the system that worked the best. So as far as a rate goes, I think when you do find some of those shops that are available, like for us, we offer a limited amount of that to the public, and it's typically roughly a little less than double what it would be for a dyno day. So if you got a shop that's $800 to $1,000 a day for a dyno test, you might expect to be $1,600 or $1,800 a day for Spintron work. It's just a little more complex and a little more involved, and takes a little bit more, knowledge and experience, maybe a little more science than just sort of the old run the engine on the dyno kind of thing, which is great. I mean, it's a necessary part of the process, but the Spintron's a little bit more involved than that.
All right, next question. A couple that are similar. Alan and Frank have got something that is in the same neighborhood. Alan says, doesn't removing the pistons change how the pressure in the cylinder acts on the valves, thereby changing the actual valve train behavior? I have high cylinder pressure acting on a 2.195 and a 172.5 valves. And then Frank says, do you use a correction factor in Spintron for harmonics produced in the combustion process? So basically the same.
So same kind of answer as before. I mean, there's no denying that those pressures are there and that they have an effect. But again, I would argue that more often than not, they probably have more of a calming effect on the valve train because they're essentially cushioning, trying to keep the valve closed or trying to force it closed. So if anything, I'd say those pressures probably don't have much of a negative effect on the actual running engine, as evidenced by the fact that, again, over the years, from the NASCAR guys and the Pro Stock guys, all the top fuelers, and of course companies like Comp Cams have found over and over again that when you find something that works really well on the Spintron, it pretty much always works really well on the engine as well. So again, there's not a really great argument for the fact that those conditions don't exist during the testing, but the fact that those conditions don't exist does not negate, the validity of finding a good package that works well. I think, going through the spring frequencies and the harmonics of an entire valve train system, getting it all working on the Spintron, pretty rare you're going to do all that work and then put it on the dyno and go, oh man, this thing's a mess, it's a wreck, it's out of control because of cylinder pressure boost or whatever. It's just something that we don't see happen. So I think it's a fair enough assessment of the valve train the way that it's currently.
Billy is out there answering questions as well. Billy, thank you very much.
That's scary.
Yeah, exactly. Well, people are asking about this, have you tried pressurized intake system on Spintron? And so that keeps coming up over and over again, I guess, with the popularity of Boost.
Yeah, same answer though. I mean, you get back to that same thing. We could easily make a fixture and use shop air and compressed air, put it in the intake system, and you go, well, I got a 2-inch intake valve, and that's, a little over 6 or 6.5 square inches or whatever times my PSI. You could do that, but you got to remember that when you have a boosted system in your running engine, that intake manifold pressure is not the only pressure the valve has to deal with. So when you simulate that by pressurizing that intake port on a Spintron, for example, you're probably farther away from the actual operating conditions than if you didn't do that, because whether if the differential pressure across that valve is just say 10 psi difference, whether it's 10 psi on one side and 0 on the other, or whether it's 100 psi on one side and 90 on the other, the valve only sees that 10 psi differential. So ignoring the exhaust side of the engine, I believe, is a mistake when people ask about boost pressure and how it affects the valve train.
Excellent. Regarding the Project Spinal Tap, Steve wants to know, was the camshaft and related parts balanced as to not introduce any unforeseen harmonics?
No, you got to think that engine ran on the dyno 11.2 or 11.3 or something like that. I think on the Spintron, I think we went to 11.7 or something crazy. Yeah. But you got to remember, the camshaft's only turning half that speed. So if we're doing 11 on the, at the crankshaft, that camshaft's only 5,500. Now, don't get me wrong, that's pretty fast. But in the grand scheme of things, the distance from the center line of any lobe or lifter or anything isn't really nearly as far as, think about like that connecting rod journal that's flinging around in there. So no, we didn't do any of that kind of stuff. No static or dynamic balancing of any of the valve train parts, surprisingly. And again, I think that speaks to the hours and hours. I think we did in total 3 or 4 sessions of me flying to Memphis to work with Billy and the guys at Comp on various efforts, and when we thought, this is the one, we finally got it right, we're going to do this. And of course, it was harder than we thought it was going to be, but none of those sessions involved balancing any of the valve train components. To be honest, it was largely Billy and Comp and their ability to quickly react and see the data on the Spintron, create a new motion, a load profile, and go make it. Oftentimes while we were at dinner, and we'd come back the next day and have something to try. So way more value in that side of things than on sort of the minuscule stuff. I'll say, we didn't want to step over $1 to pick up a dime, and I think that's where the valve train balancing stuff probably lies in the scheme of importance there.
There you go. And for those that haven't seen it, you can find the Project Spinal Tap videos out there on YouTube, and it is
watch it.
Great stuff.
Oh, you got to hear it.
Yeah.
You got to turn volume up when you go listen to.
Is that still around out there? I didn't even know anybody even noticed that happened.
It's the internet. Right, exactly. Hey, Aaron wants to know, do you find most pro stock engines use controlled loft with minimal valve bounce to make more power in pro stock applications?
Nah, not the stuff that I've worked on. Controlled loft is a great idea in concept, but in practice, it's extremely difficult to get it to be the same every time and repeat. I'm not saying that there's no loft in a pro stock engine, but it's certainly not controlled, and it's certainly not intentional, at least on any of the stuff that I've worked on.
Excellent, excellent. And more questions coming in. Of course, we've got our next video upcoming. Ben, for people who want to continue their information and go further down the rabbit hole with this subject, what do you recommend? Where do they go to continue their, the journey of knowledge?
Well, certainly not me. I'm learning as I go here, but no, I'm kidding. So we have lots of different training and courses available at EFI University, which is more than just EFI and engine tuning. It's all engine development aspects, including all this valvetrain and Spintron stuff. So obviously our website is EFI101.com. I'm all over the social media, Facebook. If you can't get a hold of me, find Billy and he'll get a hold of me. But there's a lot more to talk about, and never enough time to do it. But things like this, Engine Performance Expo, have really given us a great sort of platform to get some of it out there. And really the goal of my presentation there was to sort of plant seeds and get people thinking about what they could be doing, or what we aren't asking the right questions about yet. So the beauty of my job is I get paid to learn the things that I most want to go teach about.
Well, and there's going to be more teaching coming up, because our next video features you as well. So don't go far. We're going to dive into your wheelhouse now. Electronic fuel injection coming up. More Ben Strader. Stick around, Ben. We got questions after this is over, but we're about to talk a little EFI.
Oh, yeah.